Welcome back, and yeah, this is where. Oh, this is not nice.
Yeah.
Yeah. Okay. Okay. This is where we stop in the morning. Yeah, we were talking about what kind of a fractional. We will go there. What kind of fractional quantum Hall edge states can be gapped, and which ones cannot. And here I'm showing, still showing a integer example where, yeah, if you recall that I consider a complex fermion moving to the right and another moving to the left, and we know the mass term can gap it. And in both sides of the picture, the mass term basically maps to this cosine phi term, yeah, which is the vertex operator. And this term, by scaling dimension counting, it's relevant. So that's why at low energy, its energy dominates. And by minimizing this energy, we want to condense. Yeah, the terminology is called condense. Basically, condense all these phi's to zero. And by that, what we really mean is, like if you consider the ground state of this component, this Lagrangian, the ground state should be roughly speaking, well, in the limit where this term dominates, the ground state is the eigenstate of every operator phi x, and the eigenvalue is zero. And in this way, the creation operator of this particle is a vertex operator creating some particles will acquire an expectation value of being 1. That's why we call it condensed. And the important thing is, the reason we can do this is basically because at different position x, this operator, if you check their commutation relation, they happen to commute with each other. And okay, and then we said if you expand around this this condensed value of phi, you get a mass term which give you the correspond to the mass of in the Dirac equation description. Okay. So then another example which is ungappable, still we talk about complex fermions. If you have two flavors of a complex fermion now moving in the same direction, meaning the velocity, so here partial t both have a plus sign, and then again similarly you can write down a mass term, kind of like a mass term which couples C1 dagger and C2. And this is a free fermion theory. You can easily diagonalize the basis, and eventually you find this mass term would not be able to gap the edge states. Instead, it just shifts the momentum 0 point or energy zero energy point of these two modes. So the question is, yeah, again, in Bostonization picture, how do we understand this? Similarly, after Bostonization, yeah, now you have two modes with a free action given by the Lagrangian here, and this mass term here again mapped to a vertex operator. Yeah, because yeah, basically the vertex operator e to the I phi j is the creation, annihilation operator of fermions of the complex fermion for this flavor j. Okay. And now you have a new field which now I define as phi minus. It's basically anti-symmetric combination of these two modes. This mode again, if you calculate the scaling dimension, it's again scaling dimension 1. Again, because free fermions have scaling dimension 1/2, and this is fermion by Lian. So again, this term is relevant. It's RG relevant, and we can try whether you can get it out by playing the same story. We want to minimize this relevant energy. That's the dominant energy at low energies. And if you can also achieve a ground state which are eigenstates of operator phi minus with eigenvalue 0, then you will minimize this cosine minus cosine potential. Yeah, but now you cannot do this because yeah, if you check the commutation relation between these two fields phi, you just recall that for chiral fermion, chiral bosons, their commutation relation is kind of a non-local commutation relation, which is non-zero. And in this case, yeah, you could just check the combination of these two fields. It'll give you a non-zero combination. So that means these two operators at different position, x and x prime, they cannot have simultaneous eigenstates. So you cannot make their eigenvalue both to be 0 simultaneously. And that's basically the understanding why this theory is undouble. Basically, you cannot condense this boson field. So that's why you cannot get a mass term from expanding around that equilibrium value. Okay, so the general theory for whether it's gouplable or ungouplable, yeah, basically the above ideas can be applied to fractional quantum Hall edge states. Here, again, I'm only talking about abelian fractional quantum Hall states, which are described by Chiral Luttinger liquid. Okay, so in general, you can have density interactions which would be given bosonized into these partial x by squared terms. So these parts are all free boson parts, as we already talked about. We know how to solve them. But in addition, actually, you can also have other terms in your Hamiltonian. You can add other terms, just like the example I showed earlier. The hopping between two fermions is such a vertex operator which take this form. But there are several rules you need to satisfy for telling whether these operators can appear in your Lagrangian. So the first, basically there are, in principle there are more constraints, but I would say these two constraints are sufficient. The other constraints are contained in these two conditions. So the first condition is that any term you add in your Lagrangian or Hamiltonian has to be bosonic. Well, that's just because all the observables in our daily life are bosonic operators. So, for example, fermions, they have to, in Lagrangians, you have to have bilinears or even number of fermion operators. So they have to be bosonic. That means if I exchange these two operators, if I exchange two operators at different positions, they should be unchanged. Or that means these two operators commute. And these two operator commutes basically is saying the statistical angle for this operator is 0 mod 2 pi. Yeah, recall that earlier we talked about the statistical angle is basically the phase you gain when you exchange two vertex operators. Okay, so then the other constraint is suppose I'm considering a fractional quantum Hall state without superconductivity, then the electron charge should be conserved on the edge. So this operator cannot create additional electric charge. And the vertex operator, earlier we found it creates some electric charge by calculating the commutator with the charge density rho of the theory. And so basically the charge you created is in units of the minus E is given by this expression. So you require this expression to be 0. Also, if you consider adding superconductivity to your edge states, which is actually what I'm more interested in later of the talk, then you only require the charge you created is mod 2, is 0 mod 2. Okay. You can tunnel Cooper pairs to a superconductor that attach to the fractional quantum Hall edge state. Okay, so with that constraints, then again let's look at an example. Basically, what kind of vertex operator you can have in your Lagrangian. For the 1/3 fractional quantum Hall state, this actually requires you. Well, earlier we talked about e to the minus I5 is actually creating a charge 1/3 anion, which is not bosonic. If you want to create an electron, at least, which is fermion, at least you need to create 3 anions. So that's given by e to the negative 3 I5. But it's a fermionic operator, so this operator cannot directly enter your Lagrangian. In order to have, suppose, here in this example, if you want to add such vertex operators into the edge states, you have to add superconductivity. And the leading term you can add to the Lagrangian is this creation of 2 fermion, 2 electrons with coefficient 6. In this case, actually, you can calculate the scaling dimension of this operator. Because this large power is 6, actually, the scaling dimension of this operator is very high. It's given by 6. And therefore, if you add this interaction, this J is highly irrelevant. So in most cases, we don't talk about it. We just ignore it in Lagrangian. Okay, here is the other example, actually, which we are going to focus on in the afternoon talk. Okay, this is a two-third state, two-third fractional quantum Hall state. It's understood, as I earlier described, it's understood as an integer quantum Hall effect, integer quantum Hall state subtracting a 1/3 Laughlin state. And the Laughlin state has a K matrix which is just a number 3. If you're subtracting it, the chirality flips. So yeah, basically you get a -3. So that's the K matrix corresponding to describing the two-third fractional quantum Hall state. This is the charge vector. Each of these states have non-fractionalized objects as electrons, so the charge is 1. In this case, if you want to create electrons, yeah, basically which we require, by which we require the statistical angle to be pi. In flavor 1, you can create electron with just e to the minus I by 1. Yeah, by the way, yeah, so the sign on the exponent actually is determined by the chirality of the corresponding field. Yeah, that's because basically creating electron means creating negative charge, and by the earlier formula, you can see the sign. The sign of charge you're creating is related to the sign here, and also the sign of K matrix. If the sign of K matrix flips, you have to flip the sign also to create the electron. Okay. So in flavor 1, the creation operator is just e to the negative I by 1. That's how we Bosnize the chiral fermions. In the fractional quantum Hall state, you have to create 3 anions to get 1 electron. So the creation operator is e to 3I by 2. Okay. So in addition to density interactions, then the other interaction you can write down on the edge is I can create an electron in first flavor and annihilate an electron in the second flavor. That's a bosonic term, which is like an electron hopping between these two modes, from the integer quantum Hall state to the 1/3 Laughlin state. So yeah, in terms of vertex operator, that's your interaction. The interaction you can add in addition to your Lagrangian. That was first discussed in a Kingfisher-Pudzinski paper in '94. We are going to talk more details about the theory here. But for now, actually, this two-third example I talk about here is because first, it looks like a non-chiral theory that you have a boson moving to the right and the boson moving to the left. They both carry central charge 1, which means, yeah, basically they are equivalent, roughly speaking, equivalent degree of freedom in CFT. But basically the question is whether you can add a mass term between these two modes to gap out these edge states. And the answer is no. Basically that's a simplest example of fractional quantum Hall state that's ungappable, even if it looks like non-chiral. So in this theory, basically what the essential point is, like this interaction I add here. Yeah. This interaction I add here is charge conserving. If you want to conserve charge, then you have to create the electron and annihilate the electron, and that's the leading term is you only have this choice. But this field, if you look at this field at these different positions, they do not commute. Basically, they give you a non-vanishing result. That's because phi 2 and phi 2, when they commute to 1/3. Basically, if you remember that the commutation relation is given by coefficient k to the -1. Okay, again, apply the earlier argument. Then you cannot condense this combination of boson field to minimize this energy, even if this term is actually can be relevant, as I'll talk about later. Okay, Yeah, basically you cannot set it to 0 and expand to get a phi squared term to obtain a gap. And more people have shown actually in Michael Levin's paper and also Zhu and Wang and Xiaogang Wen's paper, they showed that even if you have superconductivity added to the two-third state, that which would allow you to have more kinds of interactions, which satisfy the bosonic condition. Braiding angle is 0 mod 2 pi, and also the charge you created is 0 mod 2. Still, you can show that any of such solutions, the fields cannot commute to 0. So this field cannot condense. That means you cannot obtain a gap. Okay, yeah, that's saying that's an important example that's ungappable. Yeah, I would say it's still quite counterintuitive, even though you might think fractional quantum Hall state by naturally they would think they have protected edge states, but it's still useful to understand why they cannot be gapped out. But here is an example that can be gapped out. That's also discussed in Michael Levin and Zhu and Wang Xiaogang paper. Okay, yeah, so these kind of studies are in general first started in the Kingfisher-Patinsky paper, and then soon by Hadan analyzing a more generic case, then then later by Michael Levin and Xiaogang group. So this example is actually probably not a practical example, because 8/9 is probably not a existing fraction in experiment, but it's a validating theory. And for this state, the electron creation operators are these two. You can create electrons in these two modes. And one can show that if you consider this interaction here with coefficients 3 by 1 and 9 by 2, then this combination of fields, they commute to each other at different positions. And therefore, this field can be condensed, and you can set this field to 0 and obtain a mass term, eventually getting out the non-chiral states. Yeah, again, this one 8/9 state has counterpropagating edge mode. Yeah, so this will be a bit counterintuitive, but this requires superconductivity because this operator creates an electron charge too. Okay, so in general, we can talk about the generic gappable condition for the fractional quantum Hall edge states. So in general, there are two requirements. The first requirement, if you want to gap out the fractional quantum Hall edge states, you have to have a non-chiral set of edge modes, which means you have equal number of right movers and left movers. Or in terms of K matrix, that means you have equal number of plus and minus eigenvalues. In that case, you can give each pair a mass term and eventually gap them out pairwisely. That's the first condition you need to satisfy. The second condition is you need to find some vertex operator interaction that you can add into this Hamiltonian. And this term has to be able to be condensed, which means this boson field has to commute with each other at different positions. And if you just do the calculation of commutation relation between these two fields, it's pretty straightforward, actually. It gave you this expression. If you still remember, this expression is exactly the conformal spin of this vertex operator, which is L K inverse times L. Okay, so basically this condition simplifies to you have to have a vertex operator with conformal spin 0. Yeah, basically whether you can find such an operator with conformal spin 0 and being bosonic and the other condition, there's a more mathematical way of finding it called Lagrangian subgroup, which I will not talk about. But basically, you can try just try term by term. That's also okay. Yeah. So I simplify this condition a little bit more. actually the requirement that the term has to be bosonic requires this L has to be the topological K matrix times some integer vector n, and also the charge, depending on whether it's superconducting or not, the charge has to be 0 or 0 mod 2, and the conformal spin of this operator has to be 0. Okay. The other common to have is actually earlier we showed that the scaling dimension of this operator is lower bounded by the conformal spin of the operator. This is still true, and actually it's an achievable limit. Basically, your scaling dimension can reach as low as the absolute value of conformal spin, and in this case, they can if the conformal spin is 0, they can go all the way to 0, and give you the mass term. Okay, any questions so far? That's actually the original plan of first part. Okay, okay, so that's the known story. So what we are interested in is basically in the case of ungappable fractional quantum Hall edge states, do you have further interesting interaction physics which can affect your transport? And the answer is yes. So that's what I'm going to focus on next. Yeah, in this part 2. Yeah, as I showed earlier, basically the 2-third state is a example of an ungappable fractional quantum Hall state. But still, the physics, there's more non-trivial physics about it, which is first studied by Kingfisher Princeton. Okay, so to understand that, actually this study, the original study of Kingfisher Princeton is motivated by experiment. Basically, they're motivated by considering the transport of the 2-third fractional quantum Hall state. So in general, if we look at the transport of fractional quantum Hall state, we can also understand them in terms of the Landau-Buttiger formula. So the idea is, again, so this is the original action. As we said, we can go to some kind of a illegal basis with some maybe irrational transformations. But the nice thing is after this transformation, which diagonalizes both K and V matrices, you get an action, you get a Lagrangian which is decoupled in different boson bases. And this new boson basis phi prime j, they have this K matrix coefficient becomes +1 or -1. So in some sense, e to the I phi j prime can be understood as an electron. So basically, in this new basis, each phi j prime behaves similar to a free fermion, which you can apply. So basically, then you can apply the Landau-Buttiger result for these illegal bases. Okay, so in general, the charge transport, the formal way is to calculate it from Kuba's formula. You can calculate the current under voltage, the current response under voltage added to the system in this way, where the operator J and rho are the current and both charge density operators of the Chiral Luttinger theory. So earlier we showed this basis in the original basis. Rho is given by this charge vector dot product with partial x phi. Partial x phi is the kind of number density of these of each mode. And by conservation of a charge, you can derive actually current J is also has a similar expression, but with partial x changed to partial t. You can change these bases into the new phi prime basis because we want to use the property that in this phi prime basis, they're similar to free fermions. As a result, you can basically, by this analogy, you can find a Landau-Buttiger formula for fractional quantum Hall edge states, where basically, if eta j is +1, then it corresponds to a right-moving free fermion, which contributes a kind of a transmission of 1. But here actually, you note that in the phi prime basis, the charge of each mode becomes T times Q, where this Q is kind of a non-universal matrix. So you have to take that into account. So now each mode carries a charge T times Q. So actually, if I look at the right moving transmission from lead I to I plus 1, it's contributed by each right moving modes with eta j equals plus 1. Okay, so each mode contributes a coefficient proportional to the square of the charge. If Q is not a transformation, it's just identity, then we call that each T is 1. So that goes back to the Bragg-Fermion case that each electron contributes coefficient 1. And for the left movers, they contribute to the I plus 1, from the I plus 1 to I with this expression. Okay, that's generically for multi-terminals. For two terminals, actually, it's slightly different from the above case, because in this case, lead 1 and lead 2, they can be connected from by either the upper edge or lower edge. So basically, essentially, every mode contributes to the Lambda-Buttiger transmission. Okay, in this case, if I look at transmission from lead 2 to lead 1, so the left movers, they can suppose they can flow on the upper edge and contribute to T12. The right movers, they can go from the lower edge. So basically, you choose the edge, and each mode will contribute. So in this case, T12 and T21 are the same, and they're just equal to the summation of all these charge contributions of all the charges. Or you can turn the summation into a matrix form, which is this formula here. But this is actually a non-universal number in general. So first, if you now solve the Landau-Buttiger equation, that will give you two-terminal conductance sigma 1, 2 being T12 times V squared of H. And this Q matrix actually is determined by both K and velocity matrix. Yeah, so for different velocity matrices, this Q is different, and actually you'll find this number is different. But only if you consider a purely chiral fraction Quang-Hao edge, in which case that means all the eta j's are plus 1, or all the eta j's are minus 1. These are all the modes on a given edge flows in the same direction. Then only in this case, sigma 1, 2, sigma 1, 2 become universal. Yeah, that's because in general, K matrix is related to Q by this relation, if you follow the derivation here. If eta is just identity matrix, then QQT becomes K inverse. And K inverse is a universal matrix just determined by the topological information and independent of the edge potential. So in conclusion, it's basically if you have both right movers and the left movers on the edge states, in general, the naive calculation from Landau-Buttiger formula will give you a non-universal sigma 1, 2. Okay. Basically, every mode adds up, their contribution adds up. So applying that to the 2-third example, actually, the simplest story is assuming that these two modes, phi 1 and phi 2, are already decoupled, has a decoupled velocity matrix. Then the first mode has K matrix coefficient 1, the second has -3. So if you calculate a sigma 1, 2, actually these two modes, although they are flowing counterpropagating on one edge, but when you look at a two-terminal conductance, it's just like a nanowire, and you don't need to distinguish between upper or lower edge. So actually the contribution of these two modes will add up. Basically, how many channels you have determines how much conductance you have in the nanowire. So by this naive argument, if the two modes are already decoupled, actually you get a sigma 1, 2, which is 1 plus 1/3, which is 4/3 times E squared of H. It should be an E squared of H. And actually, as shown by Fisher-Purczynski, you can further do a calculation of sigma xy. That's also done by Landau-Buttiger formula. That will also give you a non-universal result. But experimentally, actually, there are nice recent experiments which detects more details. in the transport of two-third fraction quantum state. And generally the result is for short edges, if this junction is very short, then indeed you have a regime where you can see sigma 1, 2 is for third. But when the edge becomes long, eventually it becomes two-third E squared of H. And two-third E squared of H is what you expect from the naively quantized Hall conductance. As earlier we said, if the edge states are purely chiral, then sigma 1, 2 and sigma xy, they're actually equal to each other. Okay, so the Kingfisher-Brzezinski paper is aimed to solve this puzzle. And what they found is, here's the summary of the result. Basically, if you consider disordered backscatterings between these two modes, that term can be relevant and drive the edge states into a new phase. Basically, under this RG flow, it flows to a new phase with still two counterpropagating modes, but one mode is carries the charge and flows to the downstream. More roughly speaking, we say the charge is two-thirds. And the backward mode becomes a charge neutral mode. So although you still have counterpropagating modes, but the backward propagating mode is actually not contributing to charge transport. And that's why eventually you would reach this sigma 1, 2 equals two-thirds as only contributed by rho. Okay, so that's what we want to show in more details. Okay, so if we consider this two-third fraction quantum Hall theory, as I already wrote earlier, with these electron creation operators, if you require the edge state to be charge conserving, that's the setup in the Kingfisher-Brzezinski paper. They're considering just the fraction quantum Hall state itself, which conserves charge. Then to the leading order, you only have this backscattering term, which is you create an electron in this mode and annihilate the electron in that mode. Okay. But the only difference from what I showed earlier is now they are considering such scatterings being strongly disordered. So this coupling strength is actually randomly depending on the spatial position X. And for their purpose, so the practical reason is because experimentally disorders cannot be avoided. And in the large sample limit, you can think of these couplings as random and short range correlated. So here, by short range correlated, the simplest approximation is to assume that these psi's are sampled from an ensemble which has a correlation. The average of the correlation is a delta function with the strength W characterizing the strength of this order. Okay, so this operator, if you look at the, if you calculate the conformal spin of this operator, so that should be K minus 1. It give you this minus 1. Conformal spin is minus 1. So that says, first, this conformal spin is not 0, so that's why the theory is ungappable. Basically, you cannot gap out the non-chiral modes. Also, it bounds the scaling dimension from below, basically to be 1. Suppose we denote the scaling dimension to be delta. Then we do a RG flow for the edge theory. So basically, if I do a rescaling of X and T, the delta, this vertex operator will scale with exponent delta. And considering the two space-time dimension, you'll find this psi, this coefficient psi flows in this way. It will scale by this e to the 2 minus delta lambda factor. At the same time, the delta function, if I do this rescaling, delta function also has a scaling dimension 1, so it scales in this way. So combining these two, and I plug this into the correlation this short-range correlation formula, then I can show this coupling strength W, this disorder strength W, has a scaling dimension 3 minus 2 delta. So if this number is greater than 0, then we say W is relevant at low energy. So we can consider this term as the dominant term at low energies. So this means the disorder W is relevant if my scaling dimension is smaller than 2/3. Sorry, 3/2. Yeah, so this is still possible because scaling dimension, the lower bound for scaling dimension is actually 1. So that's the basics of the analysis. So, okay. What Kingfisher-Patinsky paper did is, the first is more convenient to transform into a new basis. And this basis is basically eventually the mode where you flow into. So this transformation is kind of a transformation to phi prime, as I mentioned earlier, that you diagonalize the bosonic action by this transformation. But yeah, okay, but you only, it's actually a special choice which only diagonalizes the K matrix. Okay, so under this new basis, basically you can, the choice of this basis is such that here this phi rho is, phi sigma is just the combination of phi 1 plus 3 phi 2. Just recall that the disorder term is actually exactly this vertex object combination of phi 1 and 3 phi 2. And this object is a charge neutral object because you conserve charge. The vertex object does not create charge. So basically, if I redefine this phi sigma mode, this phi sigma mode is a charge neutral mode. That means the vertex object of this phi sigma does not create charge. And the rest term, you can find another basis which is orthogonal to this phi sigma basis in the sense of a K matrix product. So that's how you find these two bases. And then under this new basis, you can transform the Lagrangian into, reorganize it into 3 terms. So first, these normalization factors are chosen such that the K matrix coefficient of phi rho and phi sigma are just 1. That's just for convenience. Okay, on the other hand, now the disorder term only contains a phi sigma term. So in this way, you can see that phi rho almost do not see the disorder term. Yeah, but still, phi rho and phi sigma may couple through a velocity term, as I wrote here. If there is coupling, then everyone still feels the disorder. But disorder directly only impacts this phi sigma mode. And in general, you can, well, this is just some fact that the scaling dimension of this operator, it's a function of velocity matrix, but actually it's only a special combination of the velocity matrix, as we showed. Actually, this is a more convenient choice of parameter, which we have in our paper. Okay, so this operator, this function g, this parameter g, is non-negative. And here is a plot of the scaling dimension versus this parameter g. It reaches the minimal value, which is the conformal spin. It reaches 1 at some special parameter g, which we can find. And at this parameter, you can find that this coupling between rho and sigma would vanish at the same time. In some sense, you can see this in a reverse way. If you don't have this coupling term here, then this is just a single chiral fermion theory in terms of this phi sigma, personalizing to phi sigma. Then the scaling dimension you can calculate it just using just in a single fermion mode theory, which gives you the scaling dimension of this operator is actually 1. So in this case, it's also basically phi rho and phi sigma decoupled. So that's basically saying this is a RG fixed point because you have two decoupled modes. If you don't add the other terms, then they will never couple to each other. Okay, so what they further showed is later what they further showed is this is a stable fixed point. But before that, let's just look at the property of this RG fixed point. At this fixed point, the first point is because these two modes decouple, there's no scattering between these two modes. So phi rho is a charge mode propagating forward, so carry charge 2/3, so it gives you a transmission 2/3. While this phi sigma is decoupled, and whenever it interacts with the disorder, it does not contribute to charge transfer. So now that means this phi rho alone is responsible for transmission, and at this fixed point, you would have a two-terminal conductance being 2/3. So the upstream mode, neutral mode, is also decoupled, and there's also a way to solve this Lagrangian exactly that's given by the Kingfisher-Ptaschinski paper. It involves some understanding of these operators. So this operator e to the I squared root 2 phi sigma, it has scaling dimension 1. At the same time, partial x phi also have scaling dimension 1. So it turns out that these operators, they're actually related. So in CFT, these operators are just if you know CFT, these operators, there are 3 of them. They just form the 3 current operators of the so-called SU2 Kasmuti algebra current. But in a language we condensed matter we can understand is these operators. Yeah, so basically here you're creating or annihilating some excitations, and they actually act similar to the spin density operator of some spinful fermion, ancillary spinful fermions. They're actually not such fermions, but for purpose of calculations, it's fine to define them. So the idea is by defining 2-component fermion, I call the 2 components being a spin 1/2 or pseudo spin 1/2. Then I can look at the spin density of this fermions. That's just given by Psi-Dagger Pauli matrix and Psi. So you have 3 Pauli matrices, sigma z, sigma plus minus, and it turns out they just correspond to if you identify them with this partial x phi and e to the plus minus I square root phi, they give you exactly the same algebra. That means they satisfy the same commutation relations or any other properties of operators. In some sense, here what you're creating is a spin density. You're raising the spin density by 1 or lowering it by 1, and this partial x phi is kind of the spin density of this spin z density of this Fermi operator. And these operators have scaling dimension 1 because the scaling dimension of a free fermion in 1 plus 1d is 1/2. So that adds up to scaling dimension 1. So everything matches. So by this method, you can refermionize this action L sigma into a series like this, which is a free fermion series. So the kinetic term is just how you do the refermionization. Yeah, with some caveat. Actually, here the Hilbert space implicitly is enlarged because I only need a spin part of this fermion basis, but not the charge part of this basis. But anyway, eventually when we transform everything back, nothing is enlarged. Okay. So then this term is just sigma plus or sigma minus acting on Psi-Dagger Psi basis. Okay, so this action, recall that psi is actually spatial randomly dependent on spatial coordinate x. So this term can be eliminated by a simple transformation, fermion basis transformation, defined in the following way. If I redefine a 2x2 unitary matrix acting on psi to a basis psi tilde, this ux satisfies the condition that basically if you take partial x to its u, we give you a coefficient being this psi sigma plus and sigma minus. So in this way, if I plug this new basis, if I replace psi with a new basis, then this partial x will act on ux and give you some actual psi sigma minus and sigma plus terms. And those terms will exactly cancel this disorder term on the right-hand side. So yeah, okay. So basically after the transformation, you'll find this Lagrangian become a free fermion without disorder. But recall that this new basis psi theta is actually rotated by some random basis. Basically, because psi is random, this ux is also randomly dependent on space. Okay, and then we can rebosonize this psi theta back to the same boson mode, and boson mode by sigma theta. Then after the transformation, you'll find the Lagrangian become two decoupled free fermions without disorder. Yeah, so that's the nice story of this fixed point, which says the disorder can be completely eliminated. And basically under this new basis, you have two-third quantized sigma 1, 2, as I mentioned earlier. So the rest argument is to argue that this is a stable fixed point. Then suppose basically your disorder configuration is such that you're close enough to this fixed point. Then at low energies, this disorder term will be important and drive the edge phase into the space of a forward charge mode and backward neutral mode. So suppose now you're away from this fixed point, then you have a coupling between rho and sigma. Then actually you yeah, so in terms of fermion basis, you can rewrite the coupling term in this way. And now because ux is a random rotation in space, this coefficient is also random and short range correlated. So as a result, yeah, if you look at this coupling term, so partial x phi has given dimension 1. And this random short range correlated function, if you approximate them as correlated to a delta function, then delta function has given dimension 1. So each of these coefficients has given dimension 1/2. That's similar to the disorder scaling dimension they showed earlier. So this contributed 1/2, and also the free fermion terms has 1/2. So if you count the dimension, yeah, basically how this coefficient v rho sigma will flow, you find it's basically these scaling dimension add up to 5/2, which is larger than 2. So as a result, this v rho sigma becomes irrelevant. So it flows to 0 if you flow to low energies. That says this fixed point is stable. So this analysis, of course, is perturbative, but there's a more complete analysis done in the paper showing that as long as the disorder term, the original disorder term, before you do the basis rotation, is within the relevant gene where this vertex orbit has given dimension smaller than 3/2, then you can go to this fixed point basis and show that the RG flow here flows this coupling to 0, and basically you're flowing to the fixed point, stable fixed point. Okay, yeah, that's the summary that basically in this relevant disorder regime, eventually a two-third fraction quantum Hall state actually flows to a forward charge mode and backward neutral mode. And there's this actually motivates many other studies. There's generalization of this story to other abelian series and also non-abelian series, fraction quantum Hall states. Basically, the point is you need to have counter-propagating modes on the edge. Then once you have backscatterings between these modes, they can flow to some stable fixed point. Okay, so now basically what we are interested in is to generalize the story to superconducting fraction quantum Hall edges. Part of the reason is because recently, in the recent decades, there has been lots of progress which you can add superconductivity to the fraction quantum Hall edge states. Although the magnetic field in fraction quantum Hall state will try to tend to kill the superconductivity, but as long as your upper critical field for the superconductor is large enough, then you can still induce proximity in the fraction quantum Hall edge. Yeah, these are just some picture of the existing experiments, and they're not exactly the system we are going to consider, but this is from Philip Kim and Emil Jacobi's group. They constructed this finger superconductor coupling with the fractional quantum Hall state, also integer ones, and seem very interesting induction of superconductivity in the edge states. And there are also studies about here, like this in Finkelstein's group. Basically, what they do is you just attach a superconductor to the edge state instead of like a finger straight into the quantum Hall state. This configuration is closer to what I'm going to talk about next. This is so far only for integer quantum Hall effect. But still, there's a lot of disorders going on in the edge states. That's already understood. Yeah, so basically, the original motivation for these studies is to achieve the coherent limit of these chiral edge states. Because if there's no disorders, then in principle, these edge states, they're nice that they flow along the edge and forms a loop. So you can use them maybe to detect some interference and even braidings of particles. And this is already done in fractional quantum Hall states without superconductivity. This is in Manfred's group. They successfully measured the braiding phase of the 1/3 fractional quantum Hall state. And for superconducting states, basically the idea is if you so here what I showed is an integer quantum Hall or quantum analysis Hall edge state in proximity to superconductivity. In this case, the superconducting proximity would drive the edge states into two Majorana fermions or Bogoliubov fermions. Actually, usually in condenser, usually only call it Majorana when there's only a single mode. But anyway, mathematically they are Majorana fermions. So these modes can interfere along the edge in the electron hole space actually. So supposedly if there's no disorder, we should see nice oscillations in resistivity with respect to the edge length or whatever. But that's the reality. So this is an example of integer quantum Hall chiral edge states coupled with superconductivity. Then you would have some pairing terms between different modes. But the reality is this coupling, or it could also have backscatterings, are very random. Still, there's lots of disorders in the current experiments. So basically, like this is in Finkelstein's group experiment in their group. So they don't see very well developed oscillations. Instead, they just see some random dependence on the like Baquier and magnetic field. And basically, we have earlier work showing that basically they did statistics for the resistance they measured. This can be understood as a limit where the edge states are very disordered. But still, indeed, there are superconductivity proximity induced. So as a result, you don't see actually any nice oscillation or quantized feature of the theory. So the question is whether you can achieve quantized transport in fractional quantum Hall edge states with superconducting proximity. So this is summarizing what I'm going to talk about next in case I can't finish. But basically, we recently posted this paper showing an answer yes in the example of a nu to the 2/3 fractional quantum Hall state. And here we do not require a clean edge. Basically, we just work with the disordered superconducting proximity. And what you can show is the story is similar to the Kingfisher-Ptaschinski theory, but now with superconductivity, you have more possibility of edge backscattering couplings. And eventually, as a result, you find that there's an infinite number of RG fixed points you can flow into, depending on the velocity matrix of the edge field. And each of the theory has an downstream mode and an upstream mode, but the difference is these modes carry different charges. Here, charge is a bit hard to define because they're, for example, defined mod 2 because you're coupled to superconductor. And as a result, you can measure the downstream, so-called downstream resistance, which I'll explain what it is, you get a quantized result, which reflects this this integer qn characterizing each different fixed points. Okay, so actually with the previous introduction to the Kim-Fisher-Brzezinski theory, the rest things are mostly pretty similar, so kind of straightforward. So to start with, it's still more convenient to start from this Kim-Fisher-Brzezinski basis. That's the fixed point of the charge mode and charge neutral mode we showed earlier. Okay, in this new basis here, it's easier to tell how much charge you have for the term you added to it, because phi rho carry charge, but phi sigma does not carry charge. So the point is now with superconducting terms, now you can have terms which only conserve charge mod 2. And the most generic terms you can write down are characterized by two integers, q and p. Okay. And this operator OQP, a vertex operator OQP, in the original basis, we chose an awkward notation in the original basis because we wanted to look nicer in the new basis. But anyway, yeah, in the new basis, you can show that Q and P are just proportional to the coefficient of this phi rho and phi sigma coefficients. Yeah, of course, in the original basis, you only have integer coefficients, but in this new illegal basis, you can have rational numbers. And this Q here, this Q actually determines how much charge this operator annihilates, because phi sigma does not carry charge; it's a charge neutral object. And P has a effect on the scaling dimension. So basically, this operator would annihilate charge minus 2QE. That's saying you're tunneling Q-Kuba pairs between the edge state and the superconductor. And in general, yeah, so in general, of course, we also assume a random coefficient, which is short range correlated with zero mean. And the scaling dimension of each operator, again, yeah, that's the parameter that appears earlier as well. We find all these scaling dimensions are all functions of this single parameter, which is function of velocity matrix. Yeah, that's very convenient to work with. Okay, and the conformal spin of this operator can be, if you're sufficiently familiar with this operator now, you can clearly read it out from this expression here. It's 3q squared minus p squared. Yeah, that's basically the coefficient of this squared over 2, subtracting the square of this number over 2. And this number, by our earlier argument, it lower bounds the scaling dimension. So that's the use of this parameter. And as we analyzed earlier, if you want such a disordered term to be relevant, then we need the scaling dimension to be smaller than 3/2. And because this delta is lower bounded by conformal spin S, yeah, so we can use this conformal spin S to determine whether our operator can become relevant or not. And this conformal spin, clearly by the expression, it's an integer. So it's the only, and it cannot reach 0 because earlier we said it's ungappable edge, which is a known fact. So then this number can only be either +1 or -1 for the operator to be relevant. But actually, yeah, actually this is what Hoffman showed me that actually by considering p squared or q squared, by noting that they are 0 or 1, mod 4, that's the property of the numbers, all integers, then this number is possible to be only +1, but not -1. So this now, yeah, that means conformal spin is -1. Okay, so we need to find a solution to this equation, basically for some integer p and q, and those operators would be the possible relevant operators, which can do a similar RG flow, similar to the Kim-Fisher-Brzezinski story. And this equation is known as the Pell-Furman equation, which has known solutions in literature. The solution has a interesting expression, but yeah, basically these QNs are all integers, although they're expressed in terms of irrational numbers. And Pn, yeah, by definition, Pn is square root 3q squared plus 1. And the lowest few numbers are kind of non-trivial. It's taking these values. Yeah, so basically, this shows that only these solutions, Pn and Qn, the vertex operator corresponding to these numbers can be relevant. Basically, there are some velocity parameters where these operators are relevant. And here is a plot actually as function of the single parameter g, which is function of velocity matrix, for different operators. So here the numbers in bracket denote this Q and Pn. The scaling dimension of these each of these operators can reach 1 at different positions. Actually, in the log space, they are equally spaced. Kind of interesting fact. And this operator here with q equals 0 and p equal to 1 is the operator considered in the Kingfisher-Ptaschinski paper. But there are infinite many of them still, if you consider superconductivity. Okay, and yeah, if you happen to have a one vertex operator being irrelevant, actually you can show that all the other vertex operator will be irrelevant at the same time. So that's kind of a convenient fact that you only need to consider one relevant operator at each time. Okay, and yeah, basically the rest story is similar. But now, yeah, regarding this new operator, I want to define a new basis which make this operator to be contributed by only the upstream mode by u here. And that mode, yeah, you can do this, and that mode turns out to be related to the original Kingfisher-Ptaschinski basis in this way. Okay, and the rest story I will go faster because it's basically that follow the same as Kingfisher-Ptaschinski argument, that in this new basis of phi u and phi d, now related to the phi rho and phi sigma by another transformation, they also give you a stable fixed point. So okay, at the fixed point, yeah, you can just follow basically this upstream mode. Only the upstream mode sees the disorder. The downstream mode is already a free downstream boson, immune to disorders. But the upstream mode, this disorder terms again can be eliminated by fermionization, then doing the random spatial rotation, then bosonize it again back to a random rotated phi tilde basis. So under this transformation, eventually you flow to this free boson fixed point action, where you have a downstream mode, free boson mode, and an upstream free boson mode after random rotation. And similarly, if you do a perturbative analysis near this fixed point, you can show the coupling between upstream and downstream modes are irrelevant. So here, yeah, so it's the same analysis, so I will just skip here. Okay, so that basically leads to the final result that you have all these different, infinite number of different phases. So if you start with a velocity matrix in this regime, then it will flow to the fixed point, corresponding fixed point. So we call each of these fixed points as labeled by the corresponding integer n, labeling all the solutions, like SCN. And when n is 0, that's the Kingfisher-Ptaschinski phase studied originally in their paper. And the comment is probably among all these phases, these phases far away from the origin is actually probably hard to realize in reality. But this SC-1 phase is most promising to be realized. Basically, it requires this G to be smaller than 1. That means this V12 has to be smaller than 0. We call that V12 is the interaction or repulsion, or yeah, basically local interaction between mode 1 and mode 2. So this means you require attractive interaction between these two modes. And we would imagine maybe that's inducible by the superconducting proximity, because superconductor itself actually provides attractive interactions between electrons. That's what's exactly needed here. Okay, the rest task is to show that these fixed points actually have different quantized transport. Yeah, in terms of time, I'll go a bit faster. So there's a generalization around our Luttinger formula to the superconducting case. Actually, originally it's for nanowire, but it's similarly applied to the edge states. So the idea is, if you consider this normal metal superconductor and normal metal junction, then if some electron is incident here, then this is just a Euler scattering problem. You have some probability of reflecting as electron and as a whole, also transmitting as electron or whole. So in total, you have 4 coefficients, 4 probabilities, which add up to 1. These are known as normal reflection and drift reflection, normal transmission and drift transmission. And similarly, if you scatter from the right side, you have similar coefficients. They're not necessarily equal to the left ones. Then the transport of such a junction is determined by the following. Here, we consider the simplest case where you have 3 leads connected to the junction. So you can have current tunneling here as I1 or I2, or through the superconductor as I3. And generically, the idea is, if I look at I1, if the voltage of this lead is V1, it has voltage difference with superconductor being V1 minus VSC. So it will contribute a current proportion to this V1 minus VSC. That's the amount of the Fermi energy difference, but also proportion to this 1 minus Rn plus Ra, because if you reflect some electron, that's subtracting the conductance. But if you reflect a hole, actually you tunnel more charge, so actually it's a plus sign. And similarly, the other side, which has voltage V2, has some probability of transmitting electrons to the left side with this probability. So yeah, basically it's the difference between these two that determines the current at I1. And similarly for I2, and then by conservation of charge, the current is conserved. Yeah, so that's the generalized around our Luttinger formula. Here, every voltage is measured with respect to the superconductor, which is grounded. Right? Okay, so this is an application of that in the edge stage setup. So what we consider is, we assume that they have a 2/3 fraction quantum state. And the normal region, we assume it's in the KFP phase, which is assuming experimentally tested. When edge is long enough, it equilibrates to the 2/3 state. And in the superconducting proximity ties range, we assume it equilibrates to the SCN phase we talked about earlier, a different fixed point. Then basically, we only need to calculate these transmission and drift for normal transmission coefficients. So here, because the edge states there's only a forward propagating charge mode in the normal region. So that's indicating actually any reflection and drift reflection or normal reflection is 0. So you only have transmissions. Here, as a result, this is actually only a function of Tn minus Ta, which I call Th. And experimentally, it's conventional to measure this downstream resistance in this configuration, which is defined as I tunnel a current from lead 1 to lead 3 and measure the voltage difference between lead 2 and 3. That's just solvable by these formulas, and that's the result. And this result is nice in the sense that you can see to the leading order, Rd is proportional to Th. So basically the sign of Rd reflects the sign of Th, and the sign of Th is basically saying whether if it's positive, then electron after passing the superconductor remain mostly still as an electron. Or if it's a negative, it means you have more probability of transmitting to the other side as a whole. So yeah, basically that's why people like this Rd measurement. Its sign directly tells you whether you have efficient superconducting proximity. Okay, so when applied in our case, actually, this is some formal way to calculate it using Kuba formula. But basically, the setup is I have some incident charge in this phi rho mode, then it somehow scatters into phi b and phi u modes and still tunnel out as phi rho mode. And basically, transmission coefficient is given by this proportion to this propagator. And this propagator is similar to just like a free boson, well, not necessarily free, actually. It's just a boson propagator. And here, because partial xy are proportional to charge density, basically this characterizes how much charge density is tunneling. So basically, this is just like, again, just like a scattering problem we learned in quantum mechanics. And the important thing is to determine the boundary condition at these points. And for this boundary condition, so first, the transformation between phi sigma and phi rho is related by this matrix Rn, which I showed earlier. So that tells you these phi bases have to be related at the boundary by this transformation. That's almost by definition. But then, okay, so yeah, that's the rigorous boundary condition. But then actually, we know that this boundary condition is written in the original basis, where phi u is, we have not done the random rotation for it yet. But actually, you've done some random rotation to this phi u mode. It's actually not quite intuitive. If you first map to fermions and do the random rotation of fermion basis, then back to another boson basis. But if you look at the charge density of this, the number density of this mode, phi u, the tilde basis and the original basis are related by a random coefficient after the random rotation. So if you average out this random coefficient, actually, you can imagine whatever charge density or number density is reflected in this phi u mode will average out to 0 for long enough edge, because the correlation between these coefficients vanishes in the long range. So basically, with that basically says this upstream density, because it strongly interact with has a distorted interaction with superconductor, it keeps tunneling back and forth with the superconductor and equilibrates itself. Eventually, when it reaches the left edge, it becomes left boundary, it averages out to 0. So we can simply set this partial xy u on the left boundary at 0 for long edge. And with that, actually, that simplifies this boundary condition to a simpler relation. By setting partial xy u equal to 0, you find, basically, you can only care about these downstream modes, which are related by factor Pn, their number density. And similarly, you can find the boundary condition at x equal to L. Again, these two densities are related by the same number Pn for similar argument. Okay, with that picture, actually, it's pretty simple story then. So if you have some charge density initially incident from the left, actually what this boundary condition tells you is, after passing the first boundary, your charge density reduces to 1 with Pn factor of the original charge density. Then cross another boundary, you further reduce by a factor of 1 over Pn. So basically, this coefficient is the charge transmission, which is Tn minus Ta we talked about earlier. Because in Kubo formula, basically this tells you the current tunneling out has a transmission proportion to this 1 over Pn squared, reduced by this factor 1 over Pn squared, which is a quantized number. Then you plug this into the downstream resistance expression to find this quantized result. Okay, eventually, just another comment is actually this result would work for if Qn is not 0. Recall that Qn is the the number of Kubo pairs tunneled into the superconductor from this disordered term. So if it's really a superconducting induced phase, then Qn is non-zero, then you find this non-zero. You find this well-defined quantized RD. But actually, suppose you're not inducing an efficient superconducting proximity. That means the edge inside the superconducting range is still in the KFP phase, Kingfisher-Brzezinski phase. Then Qn is actually 0, and you'll find a diverging result. That's basically corresponding to TH equal to 1, which says basically you don't induce some efficient superconducting proximity. So in this case, actually you have to go to high orders, and eventually you'll find some nonlinear response. This RD would be proportional, being a power law related to V13. Yeah, but due to time, I will not talk about the details here. Except that I showed, actually you can also do this correction for the in the non-zero case. You also have a power law correction if you have higher voltage by a similar calculation. Okay, yeah, I will skip this part and maybe also another, yeah, okay. Just finally another comment is actually in literature there are two-third fraction quantum Hall states. The other is known as the bilayer fraction quantum Hall state. But these two states are actually topologically equivalent because they are related by a SL2Z transformation to each other. So basically, all the theory also applied to this bilayer stage as well. And here, the layer index can actually be spin index. It's not necessarily a layer index. Yeah, it just changes to a different expression for the coupling strengths in terms of the velocity matrix V prime in this bilayer case. Okay, with that, let me conclude. Yeah, maybe I'll just focus on what can be done in the future. So basically, yeah, we showed this two-third fraction quantum Hall state as an example that you have these universal points where you have kind of a new quantized transport beyond the Euro Hall connections. One of the future questions, however, actually you require the scaling dimension to be smaller than 3/2 for it to flow to this stable fixed point. So what if you're in these non-universal regimes where initially you don't have any relevant object? That's still what we need to figure out. Also, the story can be generalized to other abelian states and non-abelian fraction quantum Hall states. I think the answer is yes, and we're exploring some of the ideas. And also, yeah, basically everything topologically, the fraction quantum Hall state and fraction translators are basically quite similar. So the similar story could apply to fraction translators, maybe in Moiré systems. And yeah, that's all for my lecture. Thank you.
Interesting talk, and I think we got time for one question.
Have you ever thought about considering the dependence for the PSSCMP in this case? You have the estimation and iteration for the scaling that is linear temperature or whatever could be any temperature.
Yeah, very good question. I didn't show that, but basically the simple answer is actually, yeah. So as you see, these nonlinear response, they are for extremely low temperature when temperature is lower than the voltage, and also the voltage has to be much lower than the length scale. Yeah, I suppose. Yeah, there's also a length dependent. So if in the case that temperature becomes more dominant than V13, then basically you just replace these V13 by temperature. That's roughly the temperature dependence of these. Yeah.
Okay, so let's thank the speaker again.